Hey folks, welcome to another set of Chemistry 1 video notes. Our final unit is over heat and the ideal gas law. In our first lesson of this unit, we're going to talk about heat. By the end of this lesson, you should be able to distinguish between temperature and heat flow in both macro and microscopic terms, classify chemical reactions and phase changes as being exo or endothermic based on their enthalpy values, and use graphs to represent those energy changes, and perform calculations involving heat flow, temperature changes, and phase changes. That's a lot to learn, so let's get started. It's sometimes hard to distinguish between temperature and heat because of the vocabulary we use. We sometimes think that things are hot, so they have to have a lot of heat and a high temperature. That's not untrue, but there is a difference between heat and temperature. Temperature is a quantitative measure of how hot or cold something is. It also happens to be the average kinetic energy of the particles in a substance. Temperature, as we learned before, is an intrinsic property. A substance's temperature does not depend on how much of it there is. Heat, on the other hand, is the total kinetic energy of the particles in the substance. This is an extrinsic property. If you have more of a substance, you've got more particles with kinetic energy to add to that total. The kinetic energy of particles is also known as thermal energy. Thermal energy can move from an area of higher to an area of lower energy in one of three ways: convection, conduction, or radiation. In a liquid or gas, particles have the ability to move. When particles of high kinetic energy move from one place to another, they carry their energy with them. This movement of thermal energy is called convection. It's like when you're boiling water in a pot. The water on the bottom of the pot is hotter than the water at the top because it's closer to the heat source. Warmer water is less dense though, so it floats to the top, pushing the cooler water down. When particles come in contact with each other, they can transfer energy. This is called conduction. And it's like when the handle of the pot gets hot and you burn your hand. The energy transferred from the particles of the handle to the particles in your hand. Finally, perhaps you've got a stove whose temperature control knob is stuck on high. You might have to hold the pot up above the stove while you're boiling the water. The heat is still coming from the stove, and it's still going into the pot. But the pot and stove are no longer touching. This transfer of thermal energy from one object to another, when the objects are not touching, is called radiation. There's another word we use in this world of thermodynamics, in the study of energy in substances, and that word is enthalpy. Enthalpy is the total internal energy of a system. It cannot be directly measured, but we can measure how much it changes. In a single sample of a substance, there is energy stored within the chemical bonds between atoms. There's energy associated with the particles moving around, and that substance could absorb or release energy into its surroundings. All of those types of energy added together gives you the total internal energy of the substance, or the enthalpy of that substance. We talked about it way earlier in the year, but in order for a phase change to occur, the substance has to either absorb or release energy. If it absorbs enough energy, it's an endothermic change. These are changes like sublimation, melting, and evaporation. Notice on this chart here, all of these changes on the left side have a delta H, or enthalpy change, that is positive. They all move from a state of lower energy to a state of higher energy, which means they had to absorb energy from somewhere. If it releases energy or has a negative enthalpy change, it's exothermic. It moves from a state of higher energy to a state of lower energy, meaning it loses some of its energy. Phase changes that are exothermic are over here on the right, like deposition, condensation, or freezing. No matter the phase change, there's always a change in energy. We should know this by now. We know that solids, liquids, and gases all have different amounts of particle movement, which means that they have different amounts of energy. So there has to be a change in energy if we're moving from one state to another. In chemical reactions, that math looks a little bit different. We're going to keep it super simple this year and only focus on very basic reactions. it takes energy in order to break a bond. Think about it. If you've got two things stuck together, you have to apply energy to pull them apart. That makes the breaking of bonds endothermic. You have to add energy to it. Creating bonds is exothermic. When we bond two atoms together, they become more stable and have less energy as a bonded compound than they would as separate atoms. That energy has to go somewhere, so it gets released. When we first started in on chemical reactions, you drew particle diagrams for the before, during, and after of those chemical changes. We had certain bonds formed before. We broke all of them, so we had separate atoms during, and then we formed new ones afterwards. All chemical reactions involve this breaking and making of bonds. So when we talk about whether a chemical reaction is overall endo or exothermic, we have to understand the whole picture and do a little bit of math. So to figure out the change in enthalpy for a reaction, you look at the total energy of all the bonds in the reactants, the ones that will be broken, and then subtract from that the total energy of all the bonds in the products, the ones that will be formed. This gives you an overall enthalpy change. If it's positive, the reaction is endothermic because it gained energy. If it's negative, it's exothermic because it lost energy. Side note, if you didn't already know, we measure energy in units of joules, or sometimes, if they're really big numbers, kilojoules. So let's do an example of that. Say we want to figure out whether the reaction between hydrogen gas and chlorine gas to create hydrochloric acid is endo or exothermic. First, we need to write the reaction in a way that shows us where the bonds are. You also need to look at a chart of bond energies. The bonds that will be broken in this reaction are one hydrogen-hydrogen bond and one chlorine-chlorine bond. The energy of a hydrogen-hydrogen bond is 436 kilojoules per mole, and the energy of a chlorine-chlorine bond is 243 kilojoules per mole. Added together, our total energy of the bonds broken is 679 kilojoules per mole. On the product side, we're going to form two hydrogen chloride bonds, so we need to add that energy together twice. One hydrogen and chlorine bond is 432 kilojoules per mole. That gives us the total energy of bonds formed to be 864 kilojoules per mole. Now, take the energy of the bonds broken and subtract the energy of the bonds formed. This tells us that our enthalpy change of the reaction is negative 185 kilojoules per mole. Since it's negative, that means it lost energy, making it an exothermic reaction. We can also look at these energies on a graph. Whether it's a physical or chemical change, you'd look at the graph the same way. Start with the reactants, or the substances you started with, and look at where their energy is on the graph. Compare that to the energy of the products, or the substances you end up with. If your starting substances have less energy than your final substances, that means you added energy to the system, making it endothermic. And if your starting substances have more energy than your final substances, you took away energy from the system, making it exothermic. All right, now we're to the real fun math that I truly enjoy, because it has real practical applications that you could theoretically easily put into place tomorrow in a lab. The specific heat of a substance is the amount of heat you have to add to the substance to raise 1 gram of that substance by exactly 1 degree Celsius. That's always measured in joules per gram degree Celsius. So it's how much energy, joules, you have to add to a substance for every 1 gram and for every 1 degree Celsius. You'll be given specific heat values, or at least enough information to find them. We can use that specific heat in an equation to figure out how much thermal energy was gained or lost by a substance. That equation is Q equals mc delta T, where Q is the change in heat, m is the mass, C is the specific heat, and delta T is the change in temperature, found by taking the final temperature minus the initial temperature. That probably sounds all Greek to you. Well, there is one Greek letter in there, but it really is a fairly simple concept. Think about a metal pan. The thickness of the pan, the metal it's made out of, and how much heat you apply to it all affects how the temperature of the pan will change. If your pan is thicker, it has more mass and it takes more heat to change its temperature. If it's a metal with a relatively low specific heat, it doesn't require as much heat to change its temperature. If you add more heat, the temperature will change more. These are simple concepts that you're probably already aware of, with the exception of specific heat. You could also think of specific heat as how well a substance holds on to energy. If a substance has a low specific heat, it's a great conductor and doesn't hold on to the energy very well. If it has a high specific heat, you can try to heat it up to your heart's content, but it holds on to that energy, and when you feel it, it doesn't feel hot because it's not releasing that energy back. So let's do an example of this math. This is just one example of what you might encounter when you're asked to do calculations with this equation. Keep in mind there are 3 other variables that I can and will ask you to calculate. You'll just need to know how to do the algebra well enough to solve for them. So if we wanted to know the temperature change that results from 2,150 joules of energy being applied to 45 grams of aluminum with a specific heat of 0.895 joules per gram degree Celsius, we just plug those in to solve for the change in temperature. The energy being applied would be our heat, so Q is 2,150 joules. The mass is 45 grams. The specific heat, C, is 0.895 joules per gram degree Celsius. To solve for delta T, you divide Q by MC. So 2,150 divided by the product of 45 and 0.895 gives you a change of temperature of 53.4 degrees Celsius. Notice that number is positive. That means its temperature increased. That should make sense because we added heat to it, so it had more energy and therefore more temperature. Now this is where it gets real fun. There's a method of calculating the heat transfer from one substance to another called calorimetry. There are different types of calorimeters to measure this with, but the basic concept is you have a closed, insulated system in which no energy can get in or out. And in that system, we could use water and drop a hot or cold item into it, or we could use a reaction mixture and measure the change in temperature from the beginning to the end of the reaction. The underlying concept is this: the total energy of a closed system does not change. That means whatever energy is lost by one substance has to be gained by another. In other words, the energy or heat of one substance is equal to the negative heat of the other substance. In other words, the MC delta T of one substance will always equal the negative MC delta T of the other substance. The kinds of problems you'll do for me will involve dropping a hot or cold substance into water. When you drop a hot substance, for instance, into water, the substance will cool down, losing energy, while the water heats up, gaining energy, until they both reach the same temperature. The energy change is the same for both substances, just one's negative and one's positive. So if you know the mass of the water, the final and initial temperatures of the water, the specific heat of the water, which is always 4.184 joules per gram degree Celsius, then you can calculate the energy change of the substance you dropped in. So let's do an example. Say you drop a sample of copper, specific heat of 0.377 joules per gram degree Celsius, that has a temperature of 175 degrees Celsius, into 150 grams of water. This raises the temperature of the water from 24 degrees Celsius to 41.5 degrees Celsius. What was the mass of the copper? Well, if you'll remember, the energy of the water gained has to be equal to the energy the copper lost. In other words, the MC delta T of water should be equal to the negative MC delta T of copper. Solve for the mass of copper, and you get the mass of water times the specific heat of water times the change in temperature of the water, all over the negative specific heat of copper times the change in temperature of copper. So let's start plugging in numbers. The mass of the water was 150 grams, so plug that in for mass of water. The specific heat of water is always 4.184 joules per gram degree Celsius, so plug that in for C of water. The temperature change of the water is the final minus the initial temperatures, so 41.5 minus 24. The specific heat of copper is 0.377 joules per gram degree Celsius, so plug that in for C of copper. And the temperature change of the copper is the final minus the initial, so 41.5 minus 175. Remember, the heat transfers until both substances are at the same temperature, so the final temperature will always be the same for both substances. If you do the math on that, you should get that the mass of the copper was about 218.2 grams. Well, that's it for today, folks. I hope you learned everything you need to learn. If you have any questions, as always, let me know.